Okay, so let's look at field of quotients. So what the aim is like this. I'll put it out as a theorem. So let D be an integral domain. Then there exists a field F that, okay, so when I do this, okay, it will have a subring isomorphic to D, okay, exactly what you see in Q also. In Q actually n's are not there because they are the equivalence classes, so you're getting the n upon 1s, right? You don't have n's, in place of n's you have n upon 1s, that's the subfield anyway. So then there exists a field F that has a subring isomorphic to D, and the way in which we define this field, it will actually be the smallest field which can be proved. So what you can prove is, we will see that later also. So the way in which we are going to define it, we are going to call that field as the field of quotients of D, okay, field of quotient. The way in which we are defining this, we will actually call this, the definition of F which we are going to give is, we are going to call it as the field of quotients, okay, exact same process as what I have shown you for Q. So what we do is, first we, you can have a look at the notes for this, don't worry about making notes, okay. So what we do is, I'm going to use the same notations, take X to be the set of all A comma B such that A and B are in D, right. I am trying to create quotients of D, so A and B are in D, and what else? B is non-zero, okay. This is what I am taking X to be, okay. What's the next thing I do? Define a equivalence relation on X, okay. So define a relation tilde on X such that where A1 comma B1, I am not writing very this thing, is related. When will A1 B1 be related to A2 B2? Anyone tell me? Exactly, when A1 B2 is equal to A2 B1, that's the relation. Now I need to show that this is an equivalence relation, okay. I need to show that this is an equivalence relation. So first we will show it's reflexive. Can anyone tell me why it's reflexive? Reflexive means take an element in X and show that it's related to itself. How do I show it's related to itself? When will A comma B be related to A comma B? If AB is equal to AB, AB is always equal to AB, right? Since AB is equal to AB, always, right? The same element is always equal to itself. Since AB is equal to AB, A comma B will be related to A comma B, and therefore tilde is reflexive. Very easy to prove that this is an equivalence relation, in fact. Next, you take some A1 comma B1, I think I use A, B, C, D. Yeah, let me go with the same thing. Okay, so A, B and C, D in X such that A comma B is related to C comma D. I now need to show that CD is related to AB. Let's see what does this mean. What does this mean? It means that AD is equal to BC, right? But this means that BC, not BC, what I want, yeah, just flip the equality. So you get CB equals I've made a mistake. AD, I want to just write it in the same manner. So I want CB. So CB is equal to AB, AD, right? That's the same thing, right? If X equals Y, Y equals X. So this will mean that C comma D is related to A comma B. So very simply is symmetric. And why is it transitive? A comma B, C comma D, E comma F belong to X such that A comma B is related to C comma D and C comma D is related to E comma F. What does this mean? This means that AD equals CB, and what does this tell us? CF is related to ED. Making a mistake? No, that's fine. What do I want to show? I want to show that A times F is equal to, what is it? E times B. How do I show this? I want to show that A times F is equal to E times B. How will I show this? Multiply? You're saying multiply this to this and this to this. Okay. So what will you get? ACDF equals CBDE. Right? The D's will cancel. Right? And what else will cancel? The C will cancel, right, on both sides, which will give you exactly AF equals EB. Okay, that's exactly what we do. So this will mean multiply this left hand side to this left hand side, ADCF equals CBED, and you can cancel because we are in a integral domain, right? D is an integral domain. These are elements of the integral domain, so we can cancel. So this gives us, cancel out this C with this C, this D with this D, exactly gives us AF equals BE or EB. Let's write it as EB. Okay, and this tells us that A comma B is related to E comma F. Okay, so that's it. So this proves that this is an equivalence relation on X. So what is my field of quotients? What I expect my field of quotients to be is nothing but the equivalence classes. So we'll take F to be the equivalence classes of this relation. Let F, I'm going to denote the equivalence classes by, okay, let F be the set of equivalence. I hope everyone knows what equivalence classes are. Classes of tilde. Okay, this is the set of all the different equivalence classes. I want to show that this is a field. Okay, I want to show that this is a field. First, I need to construct the operations on it. Okay, I first need to construct the operations on it, the addition, multiplication operations in a nice manner. Okay, I need to construct it in a nice manner. So I would exactly construct it the way I construct the operations in Q. Okay, I would imitate exactly what we do in Q. Okay, that's the method we follow. So what is the operations on F? So define. We'll first define and then we'll show that what we are defining makes sense, because we will need to show that whatever we define makes sense. Why? Because there's a problem with representation. We are working with equivalence classes, right? So equivalence classes, multiple different representations, right? The representation element of an equivalence class is any element that sits inside the equivalence class. So multiple. So define plus and dot in F by, how are we defining? The elements of this I am going to call as the equivalence class of A comma B, I am going to call as A comma B bar. Okay, so what I am going to do, A comma B, someone help me, bar plus C comma D bar. What am I going to define this as? Yeah, what is it? A plus C plus comma B plus D. Is that what you are saying? So what is it? AD plus BC comma BD. That's what we do. Exactly what we do in Q, right? A upon B plus C upon D is AD plus, you all know, cross multiply, what you all call, which is not cross multiplication, which is actually AD plus BC upon BD. Okay, that's exactly what we do here. And how do we define the multiplication? What are you defining this to be? Yeah, this one is coordinate wise, right? So AC comma BD, exactly what we do in Q. Now we need to show that F with plus and dot is a field. First, we need to say that these operations are well defined. Okay, first we need to show that these operations are well defined. Let's see, I should actually do just one. So I think what I will do is, because there would be a lot of work in this. So what I think I'll do is, I will show it for plus, you show it for dot. Dot is easier than plus. Okay, so I'll show it for plus, you show it for dot. It's very simple, not difficult at all. So, so let me say plus and dot are well defined. I need to say that what is an operation? What is an operation? What do you mean by an operation? What's a binary operation? It's a function from the Cartesian product to the set. That's what it is. So I need to say that this makes sense as a function, that this is a function from F cross F to F. Okay, that means if it's a function from F cross F to F, irrespective of the representations in F cross F, you better give me back the same thing in F once you multiply. So think properly what we are doing. Okay, so plus. So let us say, suppose I'm going to give two different representations for this one and two different representations for this one. Okay, this is an element in F, element in F. So first coordinate, second coordinate, you give both of them represent. Suppose A1 comma B1 bar equals A2 comma B2 bar, which means that these two elements sit in the same equivalence class, right? That's what it means in terms of equivalence. And C1 comma D1 bar equals C2 comma D2 bar. I would need to show that the sum of these two is equal to the sum of these two. Okay. So what does this mean? This would mean that, can you see? This means that these two are related, right? They sit in the same equivalence class. the equivalence class of this and the equivalence class of this is equal, which means that these two are related. Similarly, these two are related. So this means that a1 comma b1 is related to a2 comma b2, and c1 comma d1 is related to c2 comma d2. In other words, what does this mean? a1 b2 equals a2 b1, and c1 d2 equals c2 d1. Okay, so we can replace in that manner. Okay, so what is I need to show that what is it? Yeah, operating this with this gives me what? Operating this with this gives me what? See, what I need to show that we need to show that, see, operating this with this gives us what? a1 d1 plus, what is it? Yeah, just in place of this just put 1, right? b1 c1 comma b1 d1, correct, right? Yeah, we need to show that this is related to, or this equivalence class is the same as the equivalence class of a2 d1 d2 plus b2 c2 comma b2 d2. That's the advantage of using nice notations. I need to show this, which means that I need to show that these two are related. How do I show that these two are related? When is a comma b related to c comma d? Take the numerator of this, multiply to the denominator of that, should give you the same as take the numerator of that, multiply to the denominator of this. So how do I show that? If I take this into this, it should be the same as this into this. Okay, that's all I need to do. So let's try. This into this gives me what? If you know what you are doing, then it is not very difficult. I think here you might need some, I need to get that, right? So how do I get that? So you know, in place of the a1 d1, I need to switch it with the a2 d2. So that's, let's write this out, will give me, multiply this. So a1 b2, I think some of you all will be able to see it now, into d1 d2. This one actually doesn't matter, plus let's go with b1 b2 c1 d2. Yeah, anyone? Essentially you need to switch the a1 d1 with the a2 d2. You can see that here, a1 d1, correct. I should have, what was this? What was here? What have I done? B2, right? B2, was it right? Yeah, okay. Yeah, can anyone tell me? A1? No. I'm making a mistake. That was right what I had done. A1, because I can't switch, right? That. D1, D2. Okay. How will I get this? Let's maybe otherwise look at that product also. That will make it easier, right? A2 D2 plus B2 C2 into B1 D1. This is nothing but A2 B1 times D1 D2. Now I think you should be able to see it. Then B1 B2 C2 D1. Can you now see it? What is this into this? Just this. How can we get that? Yeah, just replacing. Right? We know that these are equivalent, so you just replace. So A1 B2 is nothing but A2 B1 D1 D2 plus B1 B2 C2 D1, and we get exactly what is here, which is A2 D2 plus B2 C2 times B1 D1. Not very difficult, just very routine type of calculation. Okay, you need to go back and front and get these things. So this is what you have, which means what? It means that this is related to this, which means that these two equivalence classes are the same. Okay, which means that A1 D1 plus B1 C1 comma B1 D1 is related to A2 D2 plus B2 C2 comma B2 D2, which means that the equivalence classes, the corresponding equivalence classes are the same. Two elements are related in an equivalence relation, which means that their equivalence classes are exactly the same. Okay, you can prove, I will leave that to you. You prove that the dot is a well-defined operation. Okay, so plus is a well-defined operation. You need to prove that dot is a well-defined operation. What is the next thing to do? To actually prove that f is a field. Okay, so you have to prove that plus is a nice operation. That is, f with plus forms an abelian group. Okay, you need to prove that f with plus forms an abelian group. You need to prove that f difference 0. First you've got to choose what your 0 is. Okay, what is your 0 element? You've got to choose. It's an equivalence classes, right? Set of equivalence classes. So what will be your 0 element? So f difference 0 with dot is a abelian group, and then you need to prove that dot distributes over addition. That gives us everything for fields. Okay, so as I said again, I will do only certain parts of multiplication, but I'll do the addition part. Otherwise, because the multiplication part is actually easier, so I will leave that for you. It's on the notes, you could have a look at it. So I'm proving here that f with plus is an abelian group. So first you need to tell me what you think the identity element is. What is the identity element of this group? 0, right? What, I mean 0, what is 0? What is the 0? What do you expect? As I said, when you are thinking of f, you think of q, right? So what is the 0 element? Equivalence class of what? 0, 0. 0, 0 is not in the set X. What is it? 0, someone is saying it. What is A? Can you be more specific? Be a little more specific. 0, 1. Okay, 1 is in the integral domain, so we can talk about that. So 0, 1. The second thing is to know what that actually is, what that set actually is. We can have a look at. So we can let 0 bar be, give a good notation, right? 0 bar be the equivalence class of 0, 1. Okay, let's ask ourselves, just for the sake of making things easier, let's ask ourselves what this actually is. This is a set of all a, b in X such that a, b is related to 0, 1. What exactly is this? When is AB related to 0, 1? When? A times 1 equals B times 0. So what is that? A equals 0 and B is non-zero. Oh, I mean, I don't need to specify that B is non-zero because A, B is in X. Okay, the set of all where this happens. So this is exactly what it is. So the elements here are going to be of the form 0 comma B, where B is non-zero. Okay, the elements over here. Is this okay? What is the meaning of this? When do you say that these two are related? If A times 1 equals B times 0. B times 0 is 0, A times 1 is 1, so A equals 0. That's all this is. Okay, so this is essentially nothing but the set of all 0 comma B such that B is in D difference 0. That's all that it is. Okay, that's the equivalence class of 0. So first I need to show that the add anything to 0, I should get back the element, right? So take any element. Don't get this thing confused with notations. It's very easy. Okay, take this. I need to add this to 0. If I add this to 0, I need to show that I get back this, right? That's what I need to show. So what is A comma B plus 0 bar? This is nothing but the same as A comma B bar plus 0 comma 1 bar. What is this? By definition of addition, the definition of the addition operation, what this is? A times 1 plus B times 0 comma B times 1. What is this? If I add anything, this is also similarly you can prove the other side. Or I don't actually need to prove because I will be proving that this is abelian. So that's fine. So therefore 0 is the identity element of this group. I have not yet shown it's a group, but of that algebraic structure. Okay. Once I have this, then what are the other things I need to prove? Associativity, right? So start with some, let A comma B bar, C comma D bar, E comma F bar all belong to F. What do I need to show? Associativity. So I need to show that A comma B bar plus C comma D bar plus E comma F bar is the same as first add AB to CD and then add it to EF. Okay. So this, what I am doing here is A comma B bar plus add these, what do you get? CF plus DE comma DF bar, right? And what do you get when you add these? You will get ADF, right? I know that the multiplication and addition operations in D, these are elements of D, right? So I know the multiplication and addition operations in D are all associative, so I'm not bothered about putting the brackets here. Okay, so this plus this time this will give me BCF. I'm commuting also. If I don't do that, then it will take too long. In D I know I can commute, so I'm going to commute here. These are all elements of D. Okay, know where you're coming from. Plus BDE, BDF. That's what we get. Okay, now you want to check that this is the same as, this is how you have to work. Okay, there is a comma b bar plus c comma d bar plus e comma f bar. So add these two, what do you get? AD plus CB comma BD bar, add this to EF bar. What do you get when you add these two? It's nothing but ADF plus BCF. I am commuting elements and all that, okay? Don't worry about that because we are working in a commutative ring. D is a commutative ring, so I can do that. Plus, I think, yeah, BDE. BD. I attempted writing the elements in such a way so that it's lexicographic order. So it keeps one direction that way. And now you can see that this is the same as this. Right? This is the same as this, which means that addition operation is associative. You check this element, it's the same thing. Okay? So that means that the operation is associative. So that does with this. So therefore, plus is associative. Okay. Next, I want to know the inverse, right? What is the inverse? What do you think? What is the inverse of this element? Yeah? Which one? Addition. What is the additive inverse of this? Minus a, comma. How do I know I have minus a? Because D is a ring. Just the fact that it's a ring is sufficient for us. So minus a comma b bar is the inverse. Okay. So how do I show that? You just show, oh, I also need to show commutativity, which is, I think all of you all can prove commutative in here. That's very easy to prove. Commutative here is very easy. It just comes from the fact that D is commutative. Try and see. So a comma b bar plus minus a comma b. And once I show commutative, then I don't need to show the left inverse also. So this will give me, by definition, what is this? AB plus minus AB comma B into B. Okay, if you want to write it as B square, that's fine. What is this? What is this? 0, right? 0 times B into B bar. But I wanted to show that this is 0, right? Is this 0? Yes, because this is an element of that equivalence class. So this is one of the representation elements. So this is nothing but 0 comma 1 bar, which we have written as 0 bar. And finally, fourth, you show that this I will not do. Plus is commutative. And as a homework, you would need to show this. One is f difference the 0 bar with respect to dot is an abelian group. The only thing is you need to now tell me what is the multiplicative identity. What is the multiplicative identity here? What is the, yeah? Multiplicative identity, unity element. 1 comma 1 bar. The what do you call it? Equivalence class of 1 comma 1. That's the multiplicative identity. What is the multiplicative inverse of a comma b? So if a comma b is non-zero, what do you mean by saying that a comma b is non-zero? A comma b is not in the a comma b bar. When will this be non-zero? A comma b bar is not equal to 0 bar. What does this mean? This means that a comma b is not related to 0 comma 1. with this is not related to 0 comma 1, it means that a times 1 is not equal to b times 0. So if this is not the 0 element, this is not the 0 element if and only if this coordinate is non-zero, then you can talk about something like b upon a bar, right? So the multiplicative inverse of this will be b comma a bar. Okay, multiply out those two, you can check, because it's coordinate wise multiplication. Multiplication is coordinate wise, so that gives you 1 comma 1 bar directly. So that will be the multiplicative inverse. So this is an abelian group. I gave you what's the multiplicative identity, and finally you will need to show what? Multiplication, or let me write dot distributes over plus. That's what is left. Okay, so again, to show that dot distributes over plus, take your a, b, c, d, e, f, do one side computation, that is find what is a, b times c, d plus e, f, and then you do a, b times c, d plus a, b times e, f, and show that both these give you the same equivalence class. Okay, that's what you need to do. Okay, that will prove that this is a field. But we have only proved that f is a field, right? With this, we have only proved that f is a field. What do we need to show? That f has a subfield which is isomorphic to D. So what is that subfield which is isomorphic to D? Can anyone tell me? We have only shown that f is a field. We took some equivalence classes and defined some operations on it, and we showed that f is a field. But what did the statement say? It said that that there is a field which has a subfield isomorphic to D. Right? That's what the statement said. So what is that subfield of f which is isomorphic to D? What is the subfield of f that is isomorphic to D? Anyone? Anyone, any idea? Not subfield, I'm making a mistake. What is the subring of, did I say subfield? I don't know. What is the subring of f that is isomorphic to D? D is not a field, so you can't have that. What is the subring of f isomorphic to D? Which subring of f is isomorphic to D? Think about in Z and Q. What is the association? You will take n to, yeah? N? Someone said? N? Dot 1? No. In Q, what are the elements? They have the form n upon m, right? So what is the natural choice? Take n to n upon 1. Okay, that's the natural choice. So what are we going to do is, so take T to be, what are the elements I will take in T? I want to get the subring which is isomorphic to D. What will I take? What is it? A? No. Not AB inverse, because I am using T, then we will use S. A comma 1 bar, right? So we will take all of these equivalence classes such that A is in D. So all these distinct equivalence classes, in fact, I will directly show that this thing is the thing that will prove it. But I want to define now the isomorphism from D to S. What is the isomorphism from D to S? Define phi from D to S. Can anyone tell me what the isomorphism is? Phi of any element in D, where will I take it? A comma 1 bar. What do I need to do? 1, prove it's a ring homomorphism. Okay, it's well defined, there is no problem. 1, I need to prove it's a ring homomorphism. 2, I need to show it's 1 1, and 3, I need to show it is onto. Onto is obvious, because if you take any element from here, it's of this form. So the pre-image is obvious. So onto is obvious. Yeah. So let's show it's a homomorphism. So phi is a homomorphism. So to show that phi is a homomorphism, we'll take two elements. Let A comma B belong to D, right? And I need to show that phi of A plus B is the same as phi of A plus phi of B, and phi of A into B is the same as phi of A into phi of B. Okay. So what is phi of A plus B? By definition, what is phi of A plus B? A plus B comma 1 bar. What do I need to show that this is equal to? Am I making a mistake? Yeah. What do I need to show that this is? Phi of A plus phi of B, right? So let's compute what phi of A plus phi of B is. What is phi of A plus phi of B? This is A comma 1 bar plus A comma 1 B comma 1 bar, which is A plus B. That's what you have anyway, right? 1, right? Which is nothing but phi of A plus B. Similarly, if you look at phi of A into B, I'm correct, right? This is A times 1 plus B times 1 comma 1 into 1, which is 1. That's the definition. What is phi of A into B? It is AB times 1 bar. Also, what is your phi of A into phi of B? It is nothing but A comma 1 bar into B comma 1 bar, which is just coordinate wise multiplication, that is AB comma 1 into 1 is 1 bar, which is the same as phi of AB. So we have proved that phi is a homomorphism. Okay, phi is a homomorphism. Next we need to show that phi is 1 1 and phi is onto. That proves our result, that we have a field which D sits inside. Okay, it sits inside as a subfield. Okay, it sits inside as a see, it doesn't sit inside, the set is not the same, but there is a subring, not subfield, there is a subring which is isomorphic to D inside it. We do not distinguish, in ring theory we do not distinguish between two isomorphic rings. Okay, next is so phi is 1 1. So you can either prove directly or show that the kernel is 0, up to you. Take any element in the kernel. So let A belong to the kernel of phi. What does this mean? That means phi of A is 0 bar. What is 0 bar? 0 comma 1 bar. What does this mean? What is phi of A? A comma 1 bar. Phi of A is A comma 1 bar, right? This is equal to 0 comma 1 bar. What is the meaning of this? These two are related, right? Their equivalence classes are the same, which means that they are related, which means that when are they related? If A times 1 equals 1 times 0, that means that A times 1 equals 1 times 0, which is 0. So this means that A has to be equal to 0. A times 1 is 1 times 0, right? That's the equivalent, that's the relation. So A is equal to 0, and if A is equal to 0, that means that the only element in the kernel is 0. I have taken any element, shown that it has to be the 0 element. So therefore this tells me that the kernel of phi is nothing but just the, and what about phi is onto? So take any element in S, an element of S looks like, let what to say, let A comma 1 bar belong to S, not the correct way of doing it. So therefore what is phi of what gives me A comma 1? Phi of what gives me A comma 1? Right, these are the elements in S, right? What are the pre-images? By definition it is A. That proves that, this proves that phi is a isomorphism. Okay. So I have shown that F has a subring isomorphic to D. So let's recollect what we have shown. Given any integral domain, we showed that we can construct a field in which there was a subring which was isomorphic to D. So this tells us essentially that every integral domain sits inside a field. Okay, you can take any integral domain, push it inside a field. A very nice X. So if you have no zero divisors, what can you get? If you have no zero divisors, what can you get? You can produce inverses, right? When you have no zero divisors, you can produce inverses. That's, integral domains are rings with unity with no zero divisors. When you have no zero divisors, you can produce the inverses in this manner. Okay, that's the sense of the proof. With this we finish the first chapter. There is one more fact left which I'll throw as a homework to you, which tells us that the field of quotients, the field F defined in this particular manner, is called as the field of quotients of D. Okay, it's called as the field of quotients of D. Okay, so that is called as the field of quotients of D. The way in which we have defined is called as the field of quotients of D. So there's one homework I'll give you. Let's see who can give this to me. So one homework, small homework is, okay, so I want to say that this field of quotients is the smallest field that D sits inside. I want to say that the field of quotients is actually the smallest field that D sits inside. In other words, so let D be an integral domain and F be the field of quotients of D. The field of quotients of D. So how is this F defined? The way in which we have defined it in the theorem. Okay, if S is a field, okay, so if you have a field S and a subfield that is isomorphic to D, you should also prove that that field, a subring that is isomorphic to D, you should prove that that field also has a subfield isomorphic to F. Okay, that's what I want. So if S is a field and phi is a phi from so let's say S is a field that, so let me say that T is a subring of S that is isomorphic to D, So T is a subring of S that is isomorphic to D, then show that S has a subfield. In fact, you don't need to show it's a subfield, you just need to show that it's a subring. Has a subfield, let's call it as E, okay, that is isomorphic to F. If it has a subring isomorphic to D, it will also have a subfield that is isomorphic to S. So what this essentially tells us is that if S is inside a field, you have a field, sorry, if D is inside the field, if D is inside it, okay, this D, we are actually, this is now T, right? The one which is isomorphic to T is a subring, yeah. So this is actually T, but we know that T is isomorphic to D. If this is there, then you also have this E in fact, okay. I can actually say S has a subfield E containing T, okay. So this is going to be isomorphic, this is S, this is isomorphic to F. That proves our result. That is what we are essentially saying, that if a field contains the integral domain, it will also contain the field of quotients. That means the field of quotients is the smallest field containing the integral domain. Okay, that proves that is what I want you to show. Let's see who can do this. Very simple. Okay, I'm going to stop the video.